So the topic of this video is graphical analysis of kinematics. So basically what we're going to be doing is we're going to be using a graph to analyze motion. This is a lot like what we did in class on Tuesday. A few things before you go ahead and start this video. You're going to need some graph paper. And the problem that we're going to be using to do this graphical analysis is attached to this assignment, so you can download and print it or just download it and open it up so that you can follow along. Alright, so let's take a look. Once upon a time, there was a clown in a very high place. So here's our clown. Our clown is in a very high place. Our very high place is kind of like a roller coaster. So let's take a look. Our clown is in a high place on a roller coaster. There he is. Alright, this clown starts walking. Alright, the clown starts walking and he manages to travel 10 meters. And this is 1D kinematics, so regardless of where the clown is, he's traveling in one direction, so we're going to mark his pathway. He starts moving 10 meters. Alright, we'll say that he's at the top of the roller coaster, and he moves in one dimension along that axis right there. Alright, so this clown starts moving, and he travels 10 meters in 5 seconds. Alright, then he stops to think for 2 seconds, before traveling in a negative direction. Now, a negative direction is back the way he came. And he does that with a velocity of 1 meter per second. 5 meters. At this point in time, our clown notices you and pulls something terrible from his giant, colorful clown pocket and lunges in your direction. So clown pulls something terrible out of his pocket and he lunges for you, and he makes it 28 meters away in 6.5 seconds with his something terrible. Okay, so let's go ahead. That was our scenario. So let's break it down again. Let's consider this terrifying situation. Alright, so our clown, first he started moving in the positive direction, which just means we're setting the axis, remember, so we could decide what the positive direction is. We're choosing for this demonstration, for this problem, we're choosing to the right as the positive direction, and he moves 10 meters in 5 seconds. And then he turns around with a velocity of 1 meter per second. He travels in the negative direction 5 meters. That's when he notices you. Alright, when he notices you, he lets us all know what his true intents are. He's an evil clown with evil balloons, and he lunges toward you, covering 28 meters in 6.5 seconds. So that's our scenario. Clowns are evil. So let's consider what we can do with this data. Alright, so here's what we're going to be looking at doing with this data. We're going to graph the situation on a position versus time graph first. So if we're going to graph the situation on a position versus time graph, we don't need to consider the clown or you or what was in his colorful pocket. We're going to treat him like the spherical cow. We're going to treat him as a point-like object. So we need to set up a graph. You're going to set up a graph, and one of the first things that you need to consider when you set up a graph is you need to consider what your axes should be. So that means I'm going to have to adjust this so that there's our scatter plot all ready to go. Alright, we're doing position versus time. So position, the dependent variable, is on the y-axis. Time, the independent variable, is on the x-axis. I considered how much time this entire thing takes, and I've set my scale simply. I also considered how much the clown moves, and I've set my x-axis vertically, or my y-axis vertically. I have my grid. Time is increasing 1 second per box. Position is increasing by 2 meters per box. So now we can go back and we can graph this. Alright, so what we're going to have to do is we're going to have to consider each thing. The first thing that we're going to consider is that the clown starts walking 10 meters in 5 seconds. So he's starting, so we're establishing the start time and the start position. So I'm going to say that at time equals 0, his position was 0, like he was 0 meters away from where he started. And in 5 seconds, he was able to travel 10 meters. So that means that he made it right there in the first 5 seconds. Now at this point in time, the clown stops and he thinks for 2 seconds. So that means that 2 seconds pass on the clock, 6, 7, but the clown's position doesn't change. So that means that at second number 6 he's still standing there, and at second number 7 he's still standing there. So that's what the clown does for 2 seconds. At that point in time, he decides that he's going to walk 5 meters in the negative direction with a velocity of 1 meter per second. Now we need to think. Right? His velocity is 1 meter per second. Alright, and his distance or change in position is 5 meters, but that change in position is in the negative direction, which means that his velocity must also have been negative. Let's see how we could consider that. Alright, his change in position is 5 meters in the negative direction. The time it took is what we don't know, but we do know that his velocity was in the negative direction, which means his velocity was negative 1 meter per second. And from this equation we can solve for time. Time equals 5 seconds. Now let's say you hadn't set your velocity to a negative, you would have gotten that time equals negative 5 seconds. And since that's an impossible value for you to get, then you would know, oh, I was wrong. He was traveling in the negative direction, so his velocity must have been negative. So that means that in 5 seconds he traveled backward 5 meters. So here we're at 7, 8, 9, 10, 11, 12. That's 5 new seconds, and he traveled backward 5 meters. So that means his new position right here is 5 meters backward. At this point in time, he notices you. And when he notices you, he lunges for you 28 meters away. So that means that 28 meters away, your current position, or your x1, is 5 meters away from the origin. Your x2, when the position is over, you're going to be 28 meters away from this. Right? Your delta x is 28 meters away. So your x2 is actually going to be x2 minus 5 meters equals 28 meters. So your x2 is going to be a value of 28 plus 5 is going to be 33 meters. Alright, that's your final position. Now let's consider your time. Your change in time, or the time that has elapsed, is 6.5 seconds. Alright, you started, your T1 in this situation was 12 seconds. your T2 in this situation then has to be 18.5 seconds in order for your delta T to be 6.5 seconds. 18.5 seconds minus 12 seconds equals 6.5 seconds. Alright, so I need to make sure that my axis includes that value. So 18.5 seconds, my position is going to be 33 meters. So 33 meters at 18.5 seconds. There he is. So I have now plotted all of the clown's motion, but now I need to make a few assumptions. I'm going to say that, well, I know that from in the first 5 seconds he was able to travel 5 meters. I can make the assumption that that was uniform motion, that he traveled a smooth, continuous velocity pathway from 0 to 10 meters. I can then assume that, and I don't have to assume because he just stopped and waited here, right? So his velocity there was unchanging. It was also non-existent. He wasn't moving. Then he traveled with a steady velocity of 1 meters per second in the negative direction here. Then he saw you and he lunged forward, and we can make the assumption here that in his lunge forward he traveled with a uniform motion, a steady velocity. Alright, so that means that we could call this here section 1, this here section 2, this here section 3, and this here section 4. As long as we assume uniform motion, remember uniform motion means that acceleration equals 0, and we just went over that in the previous lecture, which you should have watched first. So if our uniform motion is 0 meters, or our acceleration is 0 meters per second, our uniform motion means that in any one of these situations the velocity was constant, so we were able to draw a smooth curve because the slope is velocity, and that's always going to be true on a position versus time graph. So we can do some analysis now. We can take a look at a few of the questions. Alright, we've graphed this situation on a position versus time graph. We can tell what the clown's velocity in the first situation, 0 to 5 seconds. Right, in the 0 to 5 second situation, situation number 1, we can determine the velocity. The velocity is going to be the slope. So it's going to be the rise over the run. The velocity equals delta x over delta t. Delta x is 10 meters minus 0 meters. I chose this position and this position. I could have also chosen any of the positions in between. It just so happens I wanted the simple one. And that's 5 seconds minus 0 seconds. So for the first situation, our velocity is 2 meters per second. In the second situation, number 2, from 5 to 7 seconds, we can also determine the clown's velocity. It's going to be the slope. Now you look at this and you go, oh, it's a horizontal line, it doesn't have a slope. Correct. We can also prove that mathematically, because position 1 is 10 meters, position 2 is 10 meters. The difference, x2 minus x1, is going to be 0 meters. And then from 7 seconds minus 5 seconds, that's t2 minus t1. So that would be 0 over 2 seconds, or 0 meters per second. Number 3. We can determine the velocity here. All right, number 3, we have what is the clown's velocity, or sorry, what is the clown's velocity in the third situation? How long did it take him? What is his final position? All right, so we can answer his final position. x2 is right there. It's 5 meters. The time it took him, well, we knew the velocity equaled 1 meter per second, and it was in the negative direction, and that's going to be x2 minus x1 over t2 minus t1. We know that his final position is 5 meters. His initial position was 10 meters, so we could say final position 5 meters minus initial position 10 meters, and that equaled our initial time, t1, was 7 seconds. We can find our t2 because our velocity is 1 meter per second. So when we solve for t2, we got 12 seconds. And we were given that his slope was 1 meter per second. One thing that you want to specify here is this is negative 1 meter per second because he's traveling in the negative direction. Also very visible because his slope is negative. Then we can find what was the clown's final velocity when he lunged for you, making all of your nightmares come true. So that means we're taking a look at the fourth situation. Alright, so we're going to find the slope or the velocity. Final position was 33 meters. Initial position was 5 meters. And then the time change was 18.5 seconds minus 12 seconds. So we get 28 meters divided by 6.5 seconds. And that gives us a value of 4.3 meters per second. That is his final velocity. Right? That's how quickly he covered this distance. Right? Notice for each of these velocities. Alright, the first one is a positive 2 meters per second because this is a positive slope. Here, it's a zero slope. Zeros aren't positive or negative. They don't have direction because they're not going anywhere. Alright, number 3, our slope is negative because the velocity is negative. And then finally, this is a positive slope, positive velocity. Alright, so when he made all of your nightmares come true, by pulling this out of his pocket. Don't ask me how he got it. He's an evil clown. I mean, look at his face. Now, we can look at what is the clown's final position. We previously determined this final position. You could also solve his final position because we know that velocity equals the change in position over the change in time. It just so happens that this problem gives us, 28 meters was the change in position. And 6.5 seconds was the change in time. So we could have calculated this 4.3 meters per second first and then used it to calculate x2 final position and t2 final time. In fact, that is exactly what we did here. We just did it in a different order. So now we can answer a couple of other questions, like what is the clown's average velocity for the whole trip? Well, average velocity, remember, is just taking the total velocity from beginning to end. So this black line right here, this represents the average velocity. This isn't what the clown actually did, it's just the average of all of his motion. So we can determine the total average velocity is going to be the overall final position minus the initial position divided by the overall time. Alright, so the overall final position is 33 meters. He started from a 0 meter position. The final time was 18.5 seconds. He started from a 0 second time. So his overall average velocity for the whole trip, which is represented by the black line graphically, then gives us 33 divided by 18.5 was 1.7 meters per second, and that is a positive average velocity because it's a positive slope here. He traveled overall net a positive amount. Alright, so that's one way to take a look at turning a descriptive situation like the clown of your nightmares into a graphical analysis and then using the graph to analyze the data. The last thing that we're going to take a look at is what would this look like if we graphed it as a velocity versus time graph. So we're going to take this position versus time graph that we did, and we're going to turn it into a velocity versus time graph. All right? And you're going to notice that we actually went through and we calculated the velocity of each situation already. All right? So situation number 1 was 2 meters per second. Situation number 2, 0 meters per second. Situation number 3, negative 1 meters per second. Situation number 4, 4.3 meters per second. This is all happening over the exact same time interval. So when we do our scary clown velocity versus time graph, our time is going to have the same scale. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Our velocity, however, along the y-axis is not going to have the same scale as position because velocity is a derived unit and it's derived from position versus time. So we need to make sure that these values fit on our scale. And so I'm actually going to make it 1. I'm actually going to make it, let's see, we'll make this 1, 2, 3, 4, negative 1, negative 2, negative 3, negative 4. So you might want to ask right now, gee, Miss B, why on earth do we have velocity in both the positive and the negative direction where our position versus time graph we only drew in the positive direction? Well, first thing I want to say is position versus time graphs aren't always going to be only in the positive quadrant. In fact, if our scary clown had started right here, and we'll say that that time 0 is and position is 0, and we set our x-axis like this, which this happens actually on a pretty regular basis. All right, so our clown starts here. Right? He could travel in the positive direction. Then he could realize that his victim, aka you, where are you? You are right here. So he could have been traveling in the positive direction when he realized his victim, you, was over here. So then he pulls out his terrible thing and then rushes over into the negative direction on the other side of the origin. In this case, that motion of first traveling this way and then turning around and traveling this way on a graph, right? It would be represented as first he started at the origin, started to travel this way, realized that you were over here and rushes through the origin to you over here, right? So that means that on a position versus time graph, you could sometimes have negative positions also. It just depends on where you set your origin and what direction your object is traveling. But be very aware of that when you're setting up your grid. You want to take a look. And since we have a negative velocity, we've made sure that our velocity versus time graph includes negatives. So first, for the first 5 seconds, he traveled with a constant velocity of 2 meters per second. So he started at 2 meters per second, and at 5 seconds, he was traveling 2 meters per second. And then for 2 seconds, from 5 seconds to 7 seconds, he had no velocity. His velocity was 0. Alright, so that means that his velocity here, we're still considering uniform motion, so we still say acceleration there is 0. And then from 5 to 7 seconds, his velocity was 0. He stood and he thought about things. Then he traveled backward in the negative direction, and he did so for 5 seconds. So 1, 2, 5. He traveled with a uniform motion of -1 meters per second for 5 seconds before realizing, oops, there you are, and rushing you. For 6.5 seconds. Do we know what he did when he got there? No. Do we want to know? No. I'd rather not wake up from that dream. So, let's consider this graph. Right? This graph shows us 1, 2, 3, 4 sections of uniform motion. You notice that we have not analyzed what's going on here. Right, at any of these transition spots. Something to consider is in real life it is impossible to instantaneously change your velocity. That means that in between here, in between traveling at a uniform 2 meters per second and stopping, there was some acceleration. Right? This changed its velocity from 2 meters per second to 0 meters per second. Here we changed our velocity from 0 meters per second to -1 meters per second. Here we changed our velocity from -1 meters per second to +4 meters per second. Right? So within these blue circles there was acceleration. It's unrealistic to say that you could instantaneously accelerate, but this is not considered in this situation. We will be looking to on Thursday at situations where acceleration does happen at time. We're going to take over time, and we're going to take a look at what that graphical analysis looks like. But this is interpreting this position versus time graph into a velocity versus time graph, which you can do for any nightmare situation that you would like. So hopefully you have these two. I'm going to expect that both of these be submitted to me. I would also like you to write your own story. It could be a short story. Alright, when I say you write your own story, alright, I want 3 different motions. Alright. The dog ran forward. The dog ran backward. The dog stopped. Alright, this would be an example of 3 separate motions. Alright, I want 3 different motions in your story. I would like you to give me for each of these motions the position, the time, the change in position, the change in time, just like we did for the scary clown. I want you to analyze position and velocity and time for each of the sections, and then I want you to turn it into a velocity versus time. On your graph paper, along with the notes that you're submitting for this, you can have 1 piece of graph paper front and back for scary clown notes, position versus velocity, and I want 1 set of notes where you're telling your story with the 3 different motions: position versus time, velocity versus time.